Well, good morning, everybody. Welcome to this Industrial Advisory Board review for WIMS 2. Like Yogesh, I'd like to welcome you. I hope that those of you who are, of course, attending from companies, you've seen many slides, and you're going to see probably a few more. I probably will be showing you twice as many slides just in my presentation as you've seen so far since this morning. But I hope that you're going to of course, understand and learn a little bit about some of the activities here in our center, and also look at the breadth of technologies and applications. It is really interesting to see where the activities and the research of the center have come. And as Ken mentioned, I think one of the reasons is that these wireless systems are finding applications in many different areas. And it's not just the electronics, of course, or the energy or the packaging, but it's all the different sensing technologies and all the different components like pumps and valves and so forth that you need in these microsystems. Indeed, the vision for our program has always been trying to put and build very small micro instruments in the palm of your hand or inside your watch or on your finger ring and so forth. And miniaturizing these systems, getting them to operate at very low power and at very affordable cost is really key to broadening their applications. One of these types of devices and sensors that all of you now own are inertial sensors, accelerometers and gyroscopes. So every one of you, if you have a cell phone, most likely own at least 3 gyroscopes and 3 inertial sensors, and most likely more than that. If you drive your car and you play in a video game and so forth, pretty much all of you own sensors, and all of these sensors, inertial sensors, accelerometers, and gyroscopes, at this point are all MEMS devices. So I've talked about this topic in the past in previous meetings, but I'd like to give you an update really on what I call now an ongoing revolution in the development of angular rate sensors or gyroscopes. So inertial sensors are used in many different applications. I'm not going to go through this list. The automotive industry has always been a pioneer in really pushing the frontiers and the early development of MEMS sensors. So airbag deployment for crash sensing in cars. There are a lot of applications in avionics, aerospace, drones, of course, nowadays, defense, space, and increasingly in commercial and consumer electronics. And again, the cell phone or video games and so forth is a very good example. But there is very heightened interest recently over the past few years in high-performance gyroscopes in particular for applications in autonomous systems, whether it's autonomous cars or drones, in augmented reality, virtual reality, and some of these other types of consumer electronic systems. And as I said, the performance that you get now in your cell phones with your inertial devices is nearly not enough for some of these new and emerging applications. So again, already motion sensors, inertial sensors are in all kinds of devices. But what we need to do is to sort of see whether we can get the performance of the current devices almost in the same form factor and similar cost, improved by perhaps an order of magnitude or maybe 4 orders of magnitude in some applications. So just for those of you, again, I've used the term gyroscope already. Sometimes they're referred to as angular rate sensors, essentially to measure rotation or rotation rate. And sometimes some of you are more familiar maybe with things like yaw rate or pitch and roll. So if you look at an airplane, yaw is just rotation left to right, and roll is left to right, up and down, and pitch, of course, the tip and the tail kind of pitching up and down. So what you want to do is you want to measure rotation rate and or rotation angle. As Yogesh mentioned, just as a reference point, the Earth rotates at 15 degrees per hour. And the gyroscopes, angular rate sensors that you use in your cell phones, they're accurate to perhaps 400, 500, 1,000 degrees per hour, in that range of several hundred degrees per hour. So what you have in your cell phones is not quite there to enable you to measure angular rotation or rotation rate of the Earth. As I said, there are many, many applications. I just want to put up this chart to highlight two things. This is bandwidth versus performance, for example, for an angular rate sensor, and the performance here is in degrees per second. Applications, whether it's platform stabilization in your cameras, video cameras and so forth, in automotive environment, head-mounted displays, VR, AR, and so forth. But the thing is, there's a lot of interest really way down here. Performance that's much better in terms of accuracy and resolution than a degree per hour with reasonable bandwidth. I'm going to come back and talk about applications in much more detail a little bit later. Now, gyroscopes and angular rate sensors have been around for a long time. As I said, they have been used in the aerospace industry. They're optical gyroscopes you can go and buy for anywhere from several $1,000s a piece to maybe more than $100,000 a piece. Atomic-based gyroscopes that are super duper accurate, spinning wheels and masses and so forth. But in the MEMS domain, in mechanical devices, vibrating structures that can mechanically vibrate and move, really have been the workhorse and the best mechanism to sense rotation. And just very quickly, for those of you maybe who are not familiar with how this could be done, there is a phenomenon called the Coriolis phenomenon that is used in all of these pretty much MEMS gyroscopes to measure rotation rate. This is essentially the same phenomenon used in gyroscopes in your cell phone. And the idea is, if you have a particle or an object that's moving, let's say, with some velocity, so here just this ball moving with a velocity v, and you rotate around this axis, z-axis, you get this Coriolis acceleration or apparent Coriolis force that is perpendicular to the plane formed by the direction of the velocity of that object and the rotation axis around which the object is rotated. So you get this Coriolis force. So if you're sitting in sort of that reference frame and this ball is moving essentially in one line and you rotate it around, let's say, the z-axis, you see that this ball is maybe veering off to the left or to the right. That is essentially what you see. And so you can measure this phenomenon. So essentially any object that moves with some velocity or some speed essentially is a Coriolis force sensor, or it could be used as a angular rate detector. So I'm going to talk about this essentially a little bit, and some of these structures, in particular some of the structures that are emerging, or some also that have been used for many, many years. And without getting into too much theoretical detail, one thing maybe is good to understand, and that is ultimately for a lot of these sensors, you want to see what is the sensor structure itself capable of measuring in terms of resolution. What is the smallest signal that this device, this sensor, can measure? And when it comes to MEMS devices, this is a very important thing, because of course MEMS devices by definition are miniature. So you lose a lot of size, volume, mass, and so forth. And so the fundamental resolution limiting parameter for a lot of these angular rate sensors or gyroscopes is what's called the Brownian noise, the mechanical noise from the device itself. And without going into the detail, this noise, which is the minimum detectable signal, is a function of a number of parameters that are really determined by the mechanical device, by this moving mass, this moving ball. And these parameters include the mass, the size of the device, the geometry, the frequency of how fast the device moves, how sharp and nice is that resonance of this device. Just like a guitar string, you know, when you move it, you can hear it, and it's a very sharp tone. The sharper that tone is, the higher the Q, and the higher the Q is, the better the resolution of the device. And how much can you move this, you know, this mass? And as you can see, in order to get better devices, you really need large mass, you need large resonant frequency, you need a very sharp resonance quality factor, and a large displacement. Unfortunately, getting a large mass and a large displacement is not something you can do in, in the micro domain. And so a lot of the devices have to rely on getting a large Q and or higher frequencies. So as I talk about these, you see that frequencies of operation typically are in the kilohertz, tens of kilohertz, hundreds of kilohertz range, because that's what you need in order to get the resolution that you need. And also you will see that the quality factors are getting pushed up higher and higher and higher. Just as another reference point, and I've shown plots similar to this in the past, if you look at the performance of MEMS gyroscopes over the past 30 years or so, it's plotted here. This is essentially the noise, what is the smallest signal that the device can sense, going anywhere from about 10,000 degrees per root hour, and nowadays down to about 10 to the minus 3 degrees per root hour. So more than 6 orders of magnitude improvement really over a span of only 30 years. And in some ways, I've sometimes said this, that we actually beat Moore's law. We are improving at 1.6 times per year, which is better than Moore's law has done. Now, of course, there's scatter around, and as you get down to closer to the limits, of course, making and keeping up that improvement is harder. So Yogesh asked me to talk about sort of this coming revolution. I call it the ongoing revolution for gyroscopes. I won't be able to get through all of the details, but what I like to just point out as I go through my presentation is focus on really all of the different key areas, especially for inertial sensors, that many groups around the world and companies are working on. First is the sensor and the sensor structure itself, and this is where I mostly will talk about today. You need to make sensors that are low noise, that are low drift. You need many of them. They need to be small, of course, low cost. Many of them need to perhaps be integrated with electronics in order to get chips that are extremely small. Increasingly, we will see, and we have seen, that many of these emerging systems have many sensors in them. As I said, the chip that's in your cell phone already has 6 inertial sensors, 3 accelerometers, and 3 gyroscopes, all in one chip. But I suspect that we're going to see more and more of these sensors integrated on the same chip, and this is essentially to make these devices more accurate, as Yogesh mentioned, for example, for the hydrophone array, and better, larger signal range. Environmental control is critical to the performance of sensors. So the main reason for why a lot of these sensors that you have in your cell phones can't provide better accuracy is that they are subject to temperature drift and things like that. And so there's a lot of work in developing packaging technologies that can maintain a very stable environment for the sensing element, so as the environment, whether it's pressure, shock, vibration changes, that the sensing element does not see that change in the environment. Packaging is critical. Many of these devices are resonating, and in order to get good resonance, you need to have them packaged in things like vacuum, and so packaging technologies are being developed and will continue to be developed. Electronics, of course, for all MEMS sensors is critical. There's a lot of work in developing higher performance interface electronics in order to read out the extremely small signals that these devices produce. Just as a point of reference, many sensors, including the sensors that deploy your accelerometers, that deploy your airbag in your car, the moving element only moves about 10 to minus 3 angstroms. Basically, it doesn't move. It moves very little, and your electronics needs to be able to detect essentially that motion. And so electronics is critical. And then there's further processing of the data, what we call signal processing electronics, for things like control, sensor fusion, auto calibration, and other things that are going to be more and more applied in these devices. Now, some of these devices, of course, need to be small as they go into your cell phone. Some of them need to be very highly accurate, and they don't need to be as small or maybe have as much power. I talked about Coriolis phenomenon. I just want to very quickly show that pretty much all of the most of the sensors, gyroscopes in particular, that MEMS gyroscopes that are used nowadays and you own in your cell phones, are based on really the very basic principle of a tuning fork. And all of you are familiar with the tuning fork. You know, if you take one of these tuning forks and you hit it, you can hear it, it rings, it's very, you know, very nice, very sharp, very specific. And it just turns out actually a tuning fork is an excellent gyroscope. The way it works is that if you just think of this tuning fork, there's a shaft, of course, there's the two tines, and then this is a little movie. If you get these two tines to move in one plane, in this case left and right, let's call that the driving mode. You're driving essentially this device into resonance. There is another mode that is called the sense mode. In this case, this is these tines now moving in and out of the plane that they form, and this is a sense mode. And so you can drive them in one mode, and if you then rotate essentially this tuning fork around its shaft, then these tines, the tines of this tuning fork will then begin to vibrate or resonate in the other mode. So whichever mode you drive, then the opposite mode is the mode that you sense. And so essentially what we do in these devices is to drive these resonator in one mode, in one particular plane, rotate around one axis, and then sense the motion around the other mode. Now the problem is the Coriolis effect that you see is extremely small. So unfortunately, we're dealing always with extremely small signals and extremely small devices. I thought it would be good to show really one of the first and now commercially and probably the most commercially successful high-performance gyros. This was work that came out of Draper Labs. This shows essentially a tuning fork. You see two squares. These two squares are resonated in the plane of the substrate, left and right, one of an anti-phase. And then if you now rotate the this device, the plane of the device around this axis, then these two masses, these two squares, the big squares that you see, will basically just move in and out of the plane of the substrate, and you can sense that motion. So this tuning fork was the basis for the gyroscope that nowadays is sold by Honeywell and a few other companies. Now here you only have two tines. If you remember, I mentioned that one of the very important parameters that you need in order to get high performance for these devices is to have a high quality factor, a very sharp resonance. So the devices in your cell phones have a quality factor of about 10, maybe 100. So that's partly why, because they're small and they have low Q, they can't operate very well. Professor Anders Schell at University of California in Irvine really has got one of the largest and the best programs on inertial sensors. There are a few slides from him. One device that his group calls the quad mass gyroscope, or the QMG, really takes this tuning fork idea to the limit in order to improve quality factor. So in this case, you have essentially four masses, and there's a little movie, and you can see that each of these pairs of masses essentially move in opposite direction, and all of this is done in order to balance out and to minimize the loss of energy, and as a result to increase the quality factor. So in this case, for example, this would be the drive motion, and if you now turn this gyroscope around the axis into the plane of the slide, then these masses will begin to move in the opposite direction. So one drive, one sense mode, and now with this quad four masses, you will see that the quality factor can increase by orders of magnitude. And in this case, actually, his group has shown that the quality factor could be as high as about 2 million at frequencies operating around a couple of kilohertz. And in fact, with this device, he's demonstrated that you can get performance on the order of about 0.09 degree per hour bias stability. Let me go back to this slide because I didn't mention size. I want to mention we're talking about now essentially a very flat, a device that's only 50 microns thick and measures only a few millimeters, a couple of millimeters on a side, that can provide stability on the order of about 0.09 degrees per hour. Again, as a reminder, the Earth rotates at 15 degrees per hour. So progress is just amazing. Now, I think I would be probably remiss if I not mention and talk about the world's still best performing mechanical gyroscope. And you probably, most of you have ridden on a plane that has had one of these gyroscopes. And this gyroscope is called the hemispherical resonant gyro, or the HRG. It's shown here. Essentially, it looks like a wine glass, and you're going to see the structure a little bit later also. This was originally developed by Delco and Delphi, and through several more acquisitions at this point, it is a device that is manufactured by Northrop Grumman. All it is a wine glass, and this wine glass can be set into motion. It could be resonated, just like when you when you hit a wine glass, you can hear it. That is essentially the resonance. And the amazing thing about this device is that it has quality factor on the order of about 30 million, and a performance that's much better than 1 millidegree per hour in terms of biostability, and resolution approaches 10 to the minus 6 degrees per root hour. So performance is amazing, and the size is only about 3-4 centimeters on a side. So again, the important thing is, can we make these devices even smaller? So this basic idea of using non-rectangular shapes, so the tuning forks that I showed you were basically just tines, but can be used non-rectangular shapes, circles, discs, eventually 3D shells to sense motion. And it turns out that actually these shells are nothing more than really maybe a more sophisticated tuning fork. Is that, for example, for the wine glass, if this is the rim of the wine glass, when you set it in motion, the wine glass rim is going to vibrate up and down and left and right. And it just turns out that these are essentially the two modes of resonance for this device. Now, if you rotate the wine glass around its stem, essentially this vibration pattern will follow that rotation rate. And so you can, by monitoring the vibration pattern, you can measure rotation angle. Now, it turns out that you don't need just to have a wine glass to do this. In fact, you can have a disc. And in the past few years, the group of Professor Farooq Ayazi at Georgia Tech developed what they call the Bulk-Acoustic wave gyro, or the BAW gyro. And all it is just a disc, about a millimeter, half a millimeter in diameter, and this disc approximately 50 microns thick. You have electrodes around the disc, and you can just set this disc in motion, except that the operation frequency is around 1 to 2 to 10 megahertz or so. But the nice thing is you can get high quality factor, but because this is now a solid disc, you can also get a performance that's much better tolerant to shock and vibration. So this shows the picture of one of these devices. The disc is in the middle, and these are all electrodes surrounding it. You can electrostatically drive this disc into motion. Again, I should mention that the motion here, we're talking about literally angstroms or maybe tens of angstroms of motion, and not microns of motion. And performance of this device, now we're talking about something that's on the order of about a millimeter or so, already is a few degrees per hour, and in fact they've shown better than a few degrees per hour in stability and also in noise. And the interesting thing is that in this plot, you don't need to look at all the detail, but this is sensitivity to vibration, and this is sensitivity to shock. Their device is right down here. These are some of the other commercial devices. So these devices are providing very high performance, but at the same time are much more tolerant to the environment. Again, in this case, obviously, you don't care about shock that much. Even if you drop your phone, you're talking about maybe a few hundred G's of shock. But in many applications, there's now a need to have shock tolerance that approaches 10 to 20,000 G. And this brings me to the work that we've been doing and I've presented in the past, and that is essentially making a miniature, actual 3D kind of a wine glass shell that has high quality. So this structure is shown here. The yellow part is a fused silica shell that is formed into literally a wine glass. In this case, we refer to this as a bird bath because the stem and the structure looks like a little bird bath that you might have in your backyard. So this device then is attached in the middle, surrounded by electrodes in order to drive it into resonance and also to sense the motion. Because it is made out of fused silica, it potentially could have very high quality factor. And the device size might be on the order of about 5 millimeter to maybe about a centimeter, in that range. Now, the way we make this three-dimensional shape is we basically use blowtorching, literally just like glass blowing. So we start with a very thin layer of fused silica. Fused silica is glass, but it's very pure, does not have any contaminants or impurities in it. We put it on on a mold. We bring down a blowtorch and take the temperature up to about 1800 degrees centigrade. At that point, the fused silica gets softened. It doesn't melt completely, it just softens up. And then as it softens up, it settles into that mold and it takes this shape. So if you look at that molded part, it looks something like this. This is now fused silica, approximately 70 to 100 microns thick in most regions, and very smooth. This particular device is approximately 5 millimeters in diameter. If you look at the cross section of this device, it looks something like this. As I said, about 5 millimeters, and thickness in the range of about 70 microns or so. In fact, actually, this can get as thin as about 15 microns in the thinnest regions. Which is amazing when you think about it. You know, just using a blowtorch, literally using a blowtorch, that you can make essentially something that's this smooth and also this delicate and be able to handle it. But we can do that. And so what we do then, we take essentially these parts and we just polish away that extra rim, that flange that's around the rim, and we end up with a little cup. And in fact, this little cup looks something like this, as in this case is about 5 millimeters across. I'd call it, it's certainly the world's smallest and probably the world's highest quality wine glass. There is no question about it, because I don't think there's a wine glass that can ring as nicely as this, as you will see in just a second. Then we mount these parts essentially on a substrate, and then we surround them with electrodes to capacitively drive and capacitively sense the motion. You can make these certainly in different sizes. This is about 1 centimeter in diameter, 5 millimeters in diameter, and about 3 millimeters in diameter, but they're basically all the same principle. Now the thing is, the larger you make them, a little bit better, the higher quality factor that you can get. Remember, I showed you the HRG from Northrop Grumman, and I mentioned that, you know, diameter of on the order of about 3, 4, or 5 centimeters, you can get quality factors approaching 20 million or higher. And so what we have now measured in our devices is in our 10 millimeter device, we have measured quality factors that are actually not as high, but for devices this small are even actually more amazing. So I talked about quality factor. The other parameter that really matters a lot is what's called the ring down time. And the ring down time, all of you know, just like your wine glass, you hit it, you know how long that ringing continues will tell you how good quality glass you have, right? You all do this when you go buy, you know, or shop for crystals. So we do the same thing. We basically measure the ring down time of these little wine glasses once we get them to resonate. So the longest we've measured is about 500 seconds for a device that's about 1 centimeter in diameter. This is the longest ring down time for any device measured at, you know, at these dimensions. Again, notice the frequency is about 5 kilohertz, and in this case the quality factor is 8 million. Other devices we've measured quality factors of about 10 million, again in devices that are about 1 centimeter in diameter. And again, this is the largest that's reported, and with this performance you can get really low noise and potentially really high bias stability. Yogesh mentioned, showed this picture before. So essentially you take these devices, we kind of take them and mount them upside down. So you see essentially a donut here surrounded by electrodes, and so the resonator is coated with metal, and then there's a small gap of about 30 or so microns that separates the electrodes from the resonator. And we've measured now, this is latest measurement, bias stability on the order of about 0.01 degree per hour. And if we can make things better by another order of magnitude, eventually you can have your essentially cell phones replace GPS in areas where GPS does not exist, and you can do inertial navigation. So let me just say a few things and I'll try to wrap up. As I mentioned before, of course, instead of just one sensor, you can have many sensors in these emerging systems. And multiple sensors, of course, not only give you multiple parameters, but also give you better reliability and maybe larger dynamic range. Again, this is work from Professor Ayazi's group. This is a chip that his group developed, approximately 6-7 millimeters on the side. And you can see that in this particular case, there are essentially 7 devices, but there are 3 accelerometers and 3 gyroscopes. Now, your cell phones are multi-sensor devices. There are 3 accelerometers, there are 3 gyroscopes, but the difference between what's in your cell phone and what this device shows is performance. So the performance of the accelerometers and the gyroscopes in this chip that his group has developed is orders of magnitude. So these gyroscopes can provide stability on the order of about 1 degree per hour. Your cell phone stability on the order of about 500 degrees per hour. Accelerometers, these chips provide on the order of about 20 microG, 10 to minus 6 G accuracy. Your cell phones, if you're lucky, about 100 millig. So in the same chip size, by using new device structures and new technologies, you can build get much better performance. Another group, Professor Andrei Shkel at University of California, Irvine, actually is taking multiple devices and mounting these on, kind of think of them as the faces of a sugar cube. Again, these are very high performance devices packed in an area of no more than about 6-7 millimeters. And accelerometers, again, performance on the order of tens of microG, and gyroscopes performance on the order of about 1 degree per hour. I won't have time to talk about environmental control, but if you want to take the performance down or improve the performance down another factor of 10 or maybe 20, one needs to control the environment that these sensors see. They don't want to see changing temperature, they don't want to see changing vibration, changing shock. Of course, we can't get rid of changing temperature, but what we could do is we can essentially package these devices in a controlled environment. And that's some work that my group has done for quite some years, and that is take the sensor, mount it on a little platform, on a little heater, in its own little room, climate-controlled room, if you wish. So even though the outside temperature around the device might change, but the temperature that the sensor sees is always constant. And when you do this, we've shown that you can improve actually performance of sensors by a factor of almost 100 in some cases. In fact, we can take sensors that are in your cell phone and just ovenize them and improve performance by a factor of 100. And in fact, there's a company that came out of Michigan called EPAC that essentially commercialized this technology for use in inertial sensors and also in crystal oscillators and timing units. Let me just say one thing about processing electronics. There's a whole lot to say, but no question that one of the ongoing activities and coming revolutions in gyroscopes and inertial sensors would be more processing of electronics, processing electronics for processing data. And one example is, again, this is from Professor Ayazi's group at Georgia Tech, is self-calibration or auto-calibration of sensors. So one of the reasons, of course, these sensors don't have the accuracy is that they drift over time. Now, if you could test them and calibrate them almost continuously, then you would not even worry about drift, right? You don't care if the sensor is very accurate. If it's just only accurate for a day and then you can calibrate it, that's all you need. And so one of the things about these miniature devices is the fact that you can, in fact, generate mechanical signals using electronic signals, and then use those mechanical signals to calibrate your device. So going back to the disc gyro that I mentioned from Professor Ayazi's group, if you have a disc, you can essentially have these actuators. Just think of these as these 4 actuators that could be used to drive the device itself into resonance. And then you can use these signals and the sensors, sense signals that you get from the sensor itself to calibrate, bias out, to improve gain, control, and scale factor, and to even get rid of some of the temperature sensitivities. And in fact, in this plot down here, without knowing the details, one thing that's interesting is you can see that this is the output of the sensor. The large signal is mechanical motion, so you're just moving the gyroscope. And this small signal is actually mechanical motion that's induced by the electronics on the chip itself, so that you can essentially superimpose additional mechanical motion and then use that mechanical motion to calibrate out the device. And in fact, they've shown that you can take devices that that are uncalibrated or calibrated only in the lab. For example, in this case, a device that might be on the order of about 50 degrees per hour. And by just doing this auto calibration, this is all electronic. You're not taking the device out of the field or out of your cell phone. It's just while it's sitting in your cell phone, you do this auto calibration and can improve the performance by almost a factor of 50. And so this is another thing that you add, another tool in your toolbox that you add in order to improve performance of these devices over time. And so this brings me to sort of, I guess, the last couple of slides, and I'll wrap up with this, is that, again, looking at gyroscopes and in particular performance, and performance measured in how much does this device drift, and what kind of noise does this have? And then you look at the range of applications. There are many applications, of course. I talked about consumer applications. So in most applications like cell phones and video games and so forth, you don't need the noise and the stability to be super high. There are applications in automotive, of course, in drones, emerging applications in drones, stability of platforms like in satellites and so forth, aerial surveying by drones, robots. There's a big set of applications, robotic systems for things like farming and so forth. Navigation, of course, in consumer applications. And then oil exploration. There are a lot of autonomous systems that need better performance, and eventually really in inertial navigation. That is, you only use inertial signals in order to navigate and move around and essentially sense position. So at least for some, maybe you don't need GPS continuously, and in particular in environments where GPS is not available, that you can continue to do navigation. And it turns out, and I've shown this plot a couple of years ago, the dots here are all commercial devices, and the smaller the dot is, the smaller the devices, and the black colors mean essentially less than $10. So you can see essentially commercial devices are less than $10, but as soon as you're getting improved performance, the dots get bigger. That means devices get bigger, and the colors aren't black anymore. In fact, they get, instead of $10, they become $100 or $1,000 or $10,000 or $100,000. Now, if you look at this plot, ideally you want to be down here. You want to be down here in this corner, because that means low drift and means low noise, and you want to have a small dot, and that's really, I think, where a lot of the effort, research effort in many places going. That's the work that we've been doing here at Michigan, is trying to push, is to get to a point where you can get performance that's about 10,000 times better than what you get in your cell phones today at about similar cost, and maybe just about the same size. And if these devices become available, we're confident that many applications will emerge. So what are the challenges? Basically the same thing. We need to, of course, manage and reduce the noise, mechanical noise of these devices, readout techniques, electronic techniques, ability to control drift to variations in things like temperature and vibration and so forth, and controlling the environment of the sensor is critical. And of course, eventually, for many of these applications, low cost and being able to produce these in high volume is critical. So with that, I thank you for your attention. There's a lot of work that's been going on here at Michigan. Current, past students, in particular, I'd like to acknowledge a few of our members of our current members of the group. Dr. Jae-Young Cho has been leading many of these efforts here at Michigan for the past more than 10 years. Dr. Barushiari, John Kwan Wu has done a lot of work in electronics and electronic systems. Tal Nagorny, he did a lot of the work on the resonators, and he's not here, but he's been replaced and by Sajal Singh, one of the current PhD students who's making these devices. Ali Darishian on modeling, Chris Boyd on electronics. And so there's a constant effort that's going on, and without the support, not only, of course, of the group, but also of our sponsors, this would not have been possible. I don't know if I have any more time, but be happy to answer any questions if there are any questions.